This video is going to focus on entropy and free energy. So you have two goals with this. Number one, you want to understand entropy and how it plays a role in determining how spontaneous your reaction is. And then number two, you have to actually understand if a reaction will be spontaneous or not. So step one, we've already talked about entropy, but just as a review, entropy is actually a measure of randomness, which seems like a very abstract idea, but it's measuring the motion of the molecules. Okay, molecules that can move more in all modes have more entropy. So it's not just heat motion, but it's any motion. There are some general underlying ideas you can use to determine what the relative entropy is for different substances. Okay. So one thing, gases have more entropy than liquids do and more than solids. So as your states of matter become further spread out and have more energy to the particles, you'll have more entropy, also more chaos. The more particles you have, also, the more entropy you have. So if you make them into smaller particles by crushing them, or if they dissociate into the ions by dissolving, that is increasing the entropy of the system. Entropy then also relates to a chemical reaction in that if you have more stuff, as in you make more particles, you'll make more entropy. So if something falls apart, dissociates, decomposes into more moles, you will have more entropy. If you're at a higher temperature, you will also have more entropy. And a general rule, if you're looking at anything, is just to understand that the less order you have, the more entropy you'll have. Okay, so the main thing's going to sum up here. The higher energy states of matter have more entropy. More particles have more energy. So if you take a particle and crush it or dissolve it, and if you take a reaction and produce more moles, you'll produce more entropy. So we've got entropy and we've got enthalpy. And these are your two concepts that go into calculating free energy. Reactions are spontaneous if they produce free energy. So for enthalpy, which is delta H, you know it's endothermic when you have a positive delta H, and it's exothermic when you have a negative delta H. And basically, in general, you will be spontaneous if you release energy. Okay, you tend to be spontaneous when you have a negative enthalpy. For entropy, which is chaos, entropy is measured in delta S, the change in chaos. Positive then is more disorder, negative is less disorder or more order. So if you have more entropy, positive S, you will be more likely to be spontaneous. So positive S's lead to spontaneity and negative delta H's lead to more spontaneity. So if we compare these two then in a chart, negative enthalpies and positive entropies are what leads us to spontaneous. So at the very bottom of this chart, you can see that negative enthalpy and the positive entropy, that will always be spontaneous. If we have the opposite, if we have positive enthalpy and negative entropy, you will never be spontaneous. There's nothing you can do. But now because enthalpy is temperature dependent, we have two different scenarios that can be spontaneous depending on the temperature. So if I have a positive enthalpy, which is a problem because I want a negative enthalpy, but I lead to more chaos, these will happen spontaneously if I'm at a high enough temperature. Okay, so if the high temperature basically leads me to enough chaos to overcome my need for energy in the first place, I can be spontaneous. The reverse, if I have a reaction that's producing enthalpy, producing heat energy, but is becoming more ordered, okay, so a negative entropy, these can happen if you're at a low enough temperature. Okay? So at a low enough temperature, we still produce energy, but the change in disorder is basically offset by this very low temperature state. So these are the rules in terms of understanding when something will be spontaneous. These are the types of rules you'll need to understand and apply to the test. Now, cool enough, there's actually an equation that you can use to calculate free energy. And you will not be using this equation on the test. I just wanted you to see it. Free energy is measured in delta G, Gibbs free energy. And this is the energy available to do work, the energy that's released in a spontaneous process. And you can see it's the change in enthalpy minus the change in entropy. And that's multiplied by the temperature because entropy can be a temperature-dependent thing. Delta G then is energy, which is kilojoules. And if you look at this reaction, you will better understand why I say you need a negative delta G for a reaction to happen. That's because if you have a negative enthalpy, a negative delta H, you're more likely to happen. And if you have a positive delta S, you're more likely to happen. So if you add those two together, you'll get a negative delta G. And negative delta G's will produce free energy and will proceed spontaneously. You can also see how these two variables relate. In a situation where I have a negative delta H, I said if the temperature is low enough, you may produce free energy to make the reaction spontaneous. And that's because the second variable there with your entropy has a temperature measurement. So if you get that temperature low enough, the change in entropy may not affect the amount of free energy produced. Okay, so that's how it's temperature related. You actually see the relationship in the variables. And we can talk about that more in class on Monday if we need to. So just looking at delta G, I already said if delta G is negative, that means the reaction will be spontaneous in the forward direction. If it's positive, it actually means it's spontaneous in the reverse direction. And when delta G is 0, when the enthalpy and entropy balance each other out, that's when we find we have a reaction that can go to equilibrium. Both reactions are happening simultaneously and equal in the two directions. So there's a basic understanding of the different concepts, enthalpy, entropy, and Gibbs free energy. We'll talk more about it in class, specifically focus on examples of how you can analyze this, because I know that's probably the most difficult part. Go ahead and do the form and have a nice night.